Welcome you all in this lecture on waveguide corners, bends and twisters. Figure 1 shows a waveguide corner. In fact, two types of waveguide corners, A and B. We'll discuss them each separately. Figure 2, for example, shows two types of waveguide bends, A and B. Figure 3 so far is concerned, it also shows us two bends A, B, and figure 3C shows us a waveguide twist. So this is all we are going to discuss. Waveguide corners, figure 1, waveguide bends, figure 2, and waveguide twisters, figure 3C. So in general, waveguide corners, bends and twisters are used for changing the direction of wave propagation, or used for changing the direction of wave propagation through a waveguide system. By some angle. Well, these can also be used for changing the polarization of wave propagating through the waveguide system. So primarily they are used for changing the direction, but yes, in some cases they can be used for changing the polarization of the electromagnetic waves. We'll see that. And as we know, for energy to move from one end of a waveguide to another end, say for example we have this as our waveguide. Let me draw a waveguide somewhere. Let us say for example we have this as our waveguide, a rectangular waveguide. This is, say for example, 1, 2. So for energy to move from point 1 to point 2 through this waveguide without reflections. So if you want the energy to move from point 1 to point 2 without any reflections, the size, shape and dielectric constants. Size, shape and dielectric constant within the waveguide because the waveguide is a hollow rectangular tube in this case, and it's usually filled with some dielectric. So dielectric within the waveguide, they must all be constant. Throughout the length of the waveguide. Any abrupt change in these parameters, for example the width, the cross-sectional area, or for example the dielectric which is inside the waveguide, if we go on changing them, or if there is an abrupt change in any of these parameters, it results in reflections and hence energy will be lost. So in order to prevent such losses from reflections especially, there must be some design equations or some fundamental things when it comes to designing these corners, bends, or for example these twists, so as to avoid these losses. So first let us discuss, let me erase it. So we discuss this corner, waveguide corner, first corner, shown in figure 1. So what we intend to do is that we tend to, from these such discontinuities, we tend to decrease the losses, or we tend to decrease the reflections. So from these discontinuities, our aim is to decrease the reflections. So this length L between these continuities, this is a continuous waveguide section, this is again another continuous waveguide section. We are connecting them by a small section of a waveguide of length L. Likewise here in figure 1b, we are again connecting them with this length L of a waveguide section, which is tapered on both sides. It's tapered on this side and it's tapered on both left and right hand sides. So this length L in both the cases should be an odd multiple of lambda g by 4, so as to avoid the reflections, where lambda g is the guided wavelength. So let me erase it. So now let us try to understand how this length 2n plus 1 odd multiple of quarter wavelength is going to reduce the reflections. Say for example there are two waves. One is this wave number 1. At this discontinuity at point A, for example, it gets reflected and comes back. Let me use a different color for the reflected wave. So this is when the wave A comes back because of the reflections at point A where we have a discontinuity. Likewise, let us assume that there is another wave which gets reflected at point number B. Now, so we have two reflected waves. One is R1, for example, and other is R2. R1 is, let me erase it. R1 is shown in blue color. This is R1, is the reflected wave. R2 is this reflected wave. So we have two waves. One in the red color, this wave, which comes back from point number B, and first wave R1 which comes back from point number A. So let us see the path difference between these two waves, R2 minus R1, at some point here after reflections. So as we can see from this figure, the red color wave has to travel, this red color wave has to travel an extra different distance of L in the forward path and L in the backward path. So it has to cover an extra length of 2L as compared to the wave which got reflected at point A. So in a nutshell, the wave which gets reflected at point B has to traverse a distance 2L more than the wave that gets reflected at point A. Therefore, the path difference between the two waves is 2L. And as has been already said, that this L should be an odd multiple of lambda g by 4, so as to avoid the reflections, where n can be 0, 1, 2, 3, so on. So let's assume n is 0. So L in this case would be lambda g by 4. So 2L, the path difference would be 2 times L, which is lambda g by 4. This in turn would be equal to lambda g upon 2. The path difference between the two waves, between the two reflected waves, therefore is lambda g by 2. Let us calculate the phase difference corresponding to this. The phase difference would be, the phase difference, as we know, phase difference is 2 pi by lambda g into path difference. So that would be 2 pi upon lambda g into path difference. Path difference is lambda g upon 2. So that means lambda g cancels, 2 and 2 cancels. The phase difference between the two waves arriving is pi radians or 180 degrees. So we know if the phase difference between two waves meeting at a point is 180 degrees, they cancel out. So these two reflected waves cancel out each other. So we don't have any reflected waves coming back to this end. So that's the idea, that we want to suppress the reflections. So for suppressing the reflections, in general, the length L has to be 2n plus 1 lambda g by 4, as is given in this equation. So let's erase it. Further, this is our this corner represented in figure 1a. Figure 1a is E-plane corner, and this is our H-plane corner. The reason is that we know if we have this as the cross section of a waveguide, we know the electric field is, for TE10 mode, it would be like this: maximum at the center and minimum at the ends. This dimension corresponds to B, this dimension corresponds to A. So we have electric field here, maximum at the center, and then it goes on decreasing towards the ends. So likewise, in case of so far as the magnetic field is concerned, the magnetic field will be like this. The magnetic field will be in this direction, perpendicular to the electric field. So if we look at this cross section, our electric field again would be, for TE10 mode, it would be like this. But the magnetic field, so far is concerned, the magnetic field would be perpendicular to it like this. Magnetic field would be in this direction. So if we look at this figure B, the plane of the magnetic field is the same as the plane of this corner. So it lies in the same plane. So that's why it's called as an H-plane corner. And likewise, in this case, in figure 1a, this is called as E-plane corner, because in this case the electric field is like this, and the electric field is same as the plane of this, lies in the same plane on which this corner lies. So this is called as a E-plane corner. The second thing that we'll discuss is waveguide bends. Figure A shows a waveguide bend, and figure 2 again shows a waveguide bend. The first is called as E bend or E-plane bend. E-plane bend. This is E bend, and this is our H bend. This is our H bend, and this is our E bend. As already said, these are also used to change the direction of a signal within the waveguide with minimal losses like reflection and distortion of fields. An E-bend, so far is concerned, an E-bend changes or distorts the E field of the propagating signal. In order to minimize the reflections, the radius of this band the radius of this band should be greater than two wavelengths. That is, R should be greater than two wavelengths, where lambda g corresponds to guided wavelength. Likewise, for an edge band, again this radius, the radius of the band should be greater than two wavelengths, lambda g corresponding to guided wavelength. So an edge band, so far is concerned, an edge band changes or distorts the H field. H stands for magnetic field. Magnetic field. Now, as I said, an E band distorts E field and H band distorts H field. For example, the first band is an H band and the second band is an E band. Now, if we look at figure B, 2B, electric field would be like this. On this cross section it would be like this. So here it would be like this. This is what happens to electric field. So it distorts the E field. Here, the first case, in the edge band, our electric field would be like this, and our magnetic field would be like, let me use another color. H field would be like this. So this is the H field that gets distorted as we move along this band. So here E field gets distorted and here H field gets distorted. It can be understood from another figure. Say for example, we have this as an E band. Here, as I said, on the cross section of a waveguide, the electric field is like this. So here it would be like this, and as we move along this band, the electric field lines change their direction. So for example, here it was vertical, now here it is horizontal. So this means this E band has also done one thing, that it has changed the polarization from vertical polarization to horizontal polarization. Horizontal. We know polarization is the direction of oscillation of the electric field vector. So it has also changed the polarization from vertical to horizontal. But most importantly, so far as the definition is concerned, an E band is something which distorts this electric field, and an H band, so far is concerned, here electric field would be like this and magnetic field lines would be in this direction, as are shown by these dotted lines. So as we can see that it is the magnetic field that gets distorted as the wave propagates through this band. That's why it's called as H band, and that's why it's called as E band. There's a rule of thumb. Let me erase it first. Well, there's a rule of thumb for identifying an E band and an H band. E stands for easy, H stands for hard. So it is easy to bend a waveguide like this than to bend a waveguide like this. So E, when we see that, yes, if we have two waveguides bends, and when we look at it, we must be able to differentiate one from the other. So E band is the band that can be easily bent. A rectangular waveguide can be easily bent in this way rather than bending it like this way. Well, all I mean is that if I have a rectangular waveguide, say for example, I have this as a rectangular waveguide. It is easier to bend it either downwards or upwards. So bend can be easily achieved. So this type of a bend is called as E bend. Now there is another possibility. Say for example, I have this as a waveguide. Let me erase it first. an E bend. And if we look downwards, this bend, as I said, is an edge bend. And as we know, say for example, I have a waveguide. Let us assume this is the waveguide, the top view of a waveguide. This would be otherwise the B. This dimension is the narrow dimension, and this is the broader dimension. This is B, and this is our A. Now, as we know, the magnetic field along the length would be something like this. It forms closed paths. This is the magnetic field, top view of the magnetic field along a waveguide. So this is the waveguide H field, and the electric field would be upwards here at this port, for example, or at this opening. So, and this is the magnetic field, magnetic field, magnetic field, magnetic field. Now, what happens in an edge bend? This is an edge bend. Now, if you can see, when we do this bending, it is the magnetic field that gets distorted here. This shows that it's the magnetic field that gets distorted where we bend it. This is also evident from this thing. This is a rectangular waveguide, and this is how the fields look like. This green color shows the magnetic field. These green arrows, let me use this blue marker, these green arrows, they indicate the direction of magnetic field within the waveguide. These green arrows, they correspond to the magnetic field. So the magnetic field, as we can, is like this. This is our magnetic field. This is our magnetic field. Now, if we look at the edge bend, this is basically the magnetic field which gets distorted, as can be seen here. The arrow direction indicates the magnetic field lines, and this is a closed circuit. As we know, these magnetic lines of force, they form closed loops. So this is a closed loop, but it is what gets affected. Otherwise, ordinarily, if we have a straight waveguide, the magnetic field would look like this. So if it is clockwise, for example, this one would be anti-clockwise, depending on the wavelength. Because after every lambda g by 2, these would change the directions. It would be clockwise in one case and anti-clockwise in the other half wavelength. So in a nutshell, an E bend distorts electric field and H bend distorts magnetic field. But in order to minimize these distortions or reflections, for that matter, the radius of these curves should be 2 times guided wavelength. Here in case of H bend, it has to be 2 lambda g. Again, this stands valid. The equation stands valid for an E bend as well. The radius has to be greater than 2 times lambda g. Another formula that's commonly used for avoiding reflections for E and H bends is, for example, the formula is R is 1.5 times B for an E bend. The radius has to be 1.5 times B for an E bend. And what is this B? The B is the cross-sectional dimension. This dimension, as we know, is A, and this dimension, as we know, is B. So for an E bend, it is 1.5 times B for E bend. And for an edge bend, for example, for an edge bend, it is the radius should be 1.5 times A for an edge bend. These values R is equal to 1.5A and 1.5B, they correspond to the minimum radius of curvature. They correspond to minimum radius of curvature. Minimum radius of curvature for avoiding reflections, for avoiding reflections, or for small reflections. So in such cases, the reflections would be very small. Now finally, we'll discuss waveguide twisters. Now before that, this is just to tell you, I'll try to explain this figure once again. So as I said, these lines, the green lines, they correspond to magnetic field. The dotted, the red color, this corresponds to electric field. Say for example, we have this as our waveguide. We are dividing it into two parts, 2 and 3. Now what happens is that this cross section, so far is concerned, this cross section, the electric field, as I said, would be something like this: maximum at the center and minimum towards the ends for a general TE10 mode. So this is how it looks. Figure 3 shows us the cross-sectional view of the electric field with maximum electric field at the center and minimum towards the ends. The density of the line shows that the electric field is stronger at the center and it goes on decreasing towards the ends. And the green lines in between, these green lines, they indicate the direction of the magnetic field, which is perpendicular to the direction of electric field. So this is what it means. So electric field is maximum at the center and it is minimum at the ends, as is shown here. Now if we have several wavelengths, what it means is that as we go along the length of the waveguide, what happens is that we have, say for example, a peak. Let me use a red marker, and before that let me erase it. So if I have a green line here as a reference line, the electric field as is indicated here along the length would be something like this. Electric field is minimum here, it is maximum here, it is maximum here. So it is like this. So this peak corresponds to dense lines, this peak corresponds to these dense lines, and this zero corresponds to no lines, as we don't have any lines here. This means the electric field is weak here. Again, the electric field is weak here, as is indicated by this point, but it is maximum here, maximum here, maximum here. At points C, A, and B, it is maximum. Now if we look at these lines, it is downward, it's maximum, but arrows point in downward direction. It is again maximum here, but arrows point in upward direction. Here it is again maximum, but arrows point in downward direction. That's what these fields indicate. That's basically the electromagnetic field variation along the length of this waveguide. Now the last thing that we'll discuss is the waveguide twisters. Waveguide twisters. So this is the last thing that we are discussing, waveguide twisters. Waveguide twist. These are used for changing the polarization of the wave propagating through the waveguide. Waveguide twist is essentially a section of a waveguide in which there is a progressive rotation along the longitudinal axis. This is the longitudinal axis, and there is a progressive rotation. As we can see, there is a progressive rotation. We are just rotating it along this axis. This is the axis of the waveguide, and there's a progressive rotation along the length, a progressive rotation along the longitudinal axis. We change the polarization of the wave. All I mean is that if the electric field here is like this, the electric field here would be like this. So it changes the polarization from vertical to, say for example, to horizontal, as can be again understood by, say for example, only one figure for the twist, so I have to explain it from this figure only. So all I'm saying is that if this is the cross section here, the cross section is like this. Let me draw the cross section. The cross section is like this. So the electric field here is vertically upwards. This is the cross section. But when I twist it, the cross section would be at this point. This is at point A, this is the cross section at point A. But at point B, the cross section would look like something this. Would be something like this. So the electric field direction at this point would be like this. So here it is horizontal, here it was vertical. So it has changed the direction of electric field from vertical to horizontal. So that's why we said that these twisters are used for changing the polarization of the waves propagating through them. Now again, to avoid reflections from this twist, the length should be an odd multiple of quarter wavelength. But in most of the cases, the length L, this length L from one port to another port, this length L along the longitudinal axis, this is kept to a minimum of 2 wavelengths. So this is all we have for the day. Good day.